Welcome back, learners. In our previous session, we have completely categorized the beams of the roof, plinth, as well as the floor beams. That is the plinth beam, the first story, as well as the second story beams. So before we move on to the design, it is our duty to prepare the Excel sheet. So now let us start the Excel sheet design for the beams. Okay, so we are designing this beam as the fixed beam. So later I'll explain how we are supposed to design this beams as the continuous beams. Okay, so now I'm following the procedure that whatever it is available here. So it's a very simple design. So while doing in the Excel sheet, in the next session I'll be explaining that how to consider the shear force, how to consider the negative bending moment, as well as how to consider the positive bending moment, and how to give the corresponding reinforcement as well as drawing. So before that, today let us prepare the Excel sheet. So that is nothing but the design of the beams. Okay, so now when it comes to the design of the beam, as usual, the first and foremost step is the grade of concrete. Okay, so we need the grade of concrete. Okay, so we need the grade of concrete. So definitely the grade of concrete, so it will be represented as FCK, and the unit of this will be Newton per mm square. Okay, so let us give the grade of concrete as 25. Okay, and since it is an input value, we are supposed to give this in the red green color. Okay, so the next that you have is the grade of steel required. So grade of steel, so usually we call them as F of Y, and that is also will be in Newton per mm square. And that let us give that as 415, that is HYSD steels, and this is also input. Okay, so the next thing that you require is the breadth of the beam and the depth of the beam. We have already finalized the breadth and depth based on the analysis. Okay, so let us consider the breadth of the beam member. So we give it as the small b, and the unit of this will be in mm. So this is also an input value. So let us give the value as 300. Okay, so the next that we required is the depth of the beam. That is, we can give instead of that you can give effective cover to the beam. Effective cover to the beam member, we give it as D dash. Okay, so effective cover D dash, and that will also be in mm. And usually we maintain 20 mm as the effective cover. Then therefore I will get the effective depth of the beam and the overall depth. Effective depth of the beam member. Okay, so that will be small d. The effective depth of the beam member, that will be small d, that will be in mm, and let us give it as 480. Okay, so let us give it as 480 mm. Okay, so then you have overall depth of the beam member, that is given as capital D, so that will also be in mm. Okay, so therefore I can give it as this as, so effective depth plus effective cover to the beam. So therefore when you add, you have to get effective cover to the beam member. Okay, so these are the effective depth, effective cover, effective depth, everything. So the next we'll be having the design bending moment to which the beam has to be designed. So the design bending moment. Okay, so design bending moment, we given it as MUB. Okay, so that will be in design bending moment. So let us keep it in the value as kilonewton meter. Okay, kilonewton meter, and let us give that value as around 250, say for example. So then next you have is the design shear force. Okay, so design shear force. Okay, the design shear force, we represent it as VU, so that will be in kilonewton. Okay, that will be in kilonewton, and let us give it as around 80, say for example, right? So then next you wanted to find out the value MUB by BD square value. Okay, MUB by VD square value of MUB by BD into D. Okay, MU by BD square value. So it is MU by BD square value. So it will not be having any unit. So what you can suppose to do is it will be equals to, I'll open two brackets. So first I want MUB, this I have to be multiplied by 10 power 6 in order to convert it from kilonewton meter to Newton mm, divided by B, you know, this one, into D is small d 2 times. Okay, so that will give you value MUB by BD square. You are getting 3.61. Okay, so MUB by BD square, you are getting around 3.61. Okay, and keep it in mind students, when it comes to the design bending moment, so you know, when we have done the tables, so we have two types of moments, positive bending moment and the negative bending moment. Okay, positive bending moment and the negative bending moment. So therefore what we will do is we will categorize into the two parts. Okay, the positive bending moment and the negative bending moment. So therefore let us do that later. Okay, so therefore what I will do is I will make it into two categories now. Okay, so what we will do is we will just shift this to yeah, we will do one thing, we will just delete this column, we will delete the shear force. Okay, so let us have an insert one column here, right? I'll give the design shear force. Okay, so design shear force for the beam, which will be taken as VU. Okay, and it will be, you know, it will be in kilonewton. Okay, it will be in the kilonewton, and let us give that value as 80, right? So now when it comes to the design bending moment MUB, so let us delete this. Okay, so let me insert two columns, one here. Okay, so let me make it as one common row here. So let us merge this. So let us make it bold and black, because in this I'll be having the two values. One will be the A1, the first one will be, that is design positive bending moment. Okay, so positive design bending moment, and the second one will be negative design bending moment. Okay, so these are the two values. So both will be anyhow, it will be in kilonewton meter only, so no issues. So both will be same kilonewton meter only, but only its value is going to change. Like for example, for the one, if it is, I'm taking the positive as 200, so the one, let us take it as the negative as 100. So just for sake of example. Similarly, the value of mu by bd square, so you write it positive, and same thing you just copy here, but here you make it negative. Okay, negative. So here, while doing that, you are supposed to do 2 times, right? So mu by bd square, you are supposed to do 2 times. Okay, for the positive, you just take this into 10 power 6 divided by b d d. Okay, and whereas for this it will be it is mu into, sorry, not into, divided by b right. So these are the values of mu by bd square for the positive and negative. So once you get the value of mu by bd square, so you have to go to the corresponding SP16 table. Definitely I will show you what is the, in that get the percentage of steel. Even for the percentage of steel also, so what you can do, you can go to that value, the percentage of steel, for positive, I'll give it as PT. Similarly, the same thing, but the percentage of steel will be for the negative one. Okay, so the percentage of steel, you know, definitely it will be in the form of percentage, correct? Yes, so this will be percentage, and this will be percentage. Okay, so this you are supposed to give the value from the table. Okay, this you are supposed to give the value from the table. So just for the sake of understanding, let me give you 1.2% as well as 0.8%. Okay, just for the sake of understanding, I am getting the percentage of steel. So once you get the percentage of steel, then you are supposed to find out area of the reinforcement. So again, that will be for the positive and negative. Area of the reinforcement, positive. Okay, so we call it as AST, and same thing, but it will be for the now negative. It will be for the negative. So this will be definitely mm square. This also it will be mm square. So in order to get that, what you are supposed to do, you get equals this by 100 into, so B into capital D. Okay, yes, so that will give you the corresponding area. Similarly, so this will be 0.8 into, sorry, not into, by 100 into B into D, right? So that will be the area of reinforcement, positive and negative. So once you get the area, then you are supposed to decide the area of diameter that you are going to provide, whether you will provide the same reinforcement for both positive and negative moments or for the different. So for this, now let us assume both as the same. Okay, diameter of the reinforcement, again positive. Next you have negative. Okay, positive, next you have negative. So this anyhow, you know, I can go to the insert and it will be the diameter symbol. Similarly here also diameter symbol. Okay, yes, so definitely it will be in mm, and even this will be also in mm. Let us take that I'm going to provide 16 mm both. Okay, 16 mm I'm going to provide. So then next, you know, before I find out the number of bars, I need the area of the one reinforcement. Okay, so I'm providing area of the individual reinforcement, again positive. Next is negative. Okay, so here again I can write it as small a st. Okay, small a st I have supposed to write a st. Here also a st. So that will be mm square. So for that, you know, it is nothing but 3.142 by 4 into 16 into 16. Okay, similarly it will be equal to 3.142 by 4 into 16 into just a minute, 16 into 16, right? Yes, so that will be the individual area. So the next you want is the number of reinforcement required. Okay, so that means I'm supposed to provide now number of reinforcement required in positive side. Same thing, you want the number of reinforcement required in the negative side. Okay, so no unit for that. In order to calculate that, you are supposed to find out equals to, okay, so this divided by this. Okay, similarly for this one it will be this this divided by this. Okay, so it will be the numbers, right? Yes, so then you can find out of that. So instead of telling that number of reinforcement required, so next you can say that number of reinforcement provided. provided, because we cannot have the uneven numbers, so therefore we are supposed to make it. So let us make this as 10 and let us make this as 6, just for the sake of example I am giving. So once this is got, so the next that you are supposed to do is you are supposed to check for the shear, right? So that one, if you see that nominal shear stress you have, okay. So let us see that how we will have to do the check for the shear. Anyhow, we will do that in the next session. You'll be having the shear force, you will be dividing that by the area will give you the shear stress. Then you find out the percentage of steel that you are going to provide. So from the percentage of steel and from the grade of concrete, find out the permissible shear stress TOC value from the table 19 of IS 456-2000. So you will get the TOC value. If your TOC value is less than the TOV, that is the nominal shear stress, then definitely you have to design the shear reinforcement. If your TOC value, that is permissible shear stress, is more than the nominal shear stress, no need to design the shear reinforcement, but you are supposed to provide minimum shear reinforcement. Then along with that, you will suppose next to the table 19, in the table 20, you have a permissible shear, you have a permissible that is maximum shear stress value based on the grade of concrete, and your maximum shear stress value at any cost should not be more than the nominal shear stress. That is, your TOV should not be more than TOC max. If it is not more than TOC max, then your design is okay. If you are getting the TOV greater than TOC max, it is not allowable because it leads to the brittle failure of concrete. You are supposed to go to the redesign of the beam. So once you get that, you will find out the strength of the concrete that it is going to take, that is VUC value. Then the shear to be carried by the steel. In order to design the stirrups, you will calculate VUS. Then you finally find out the spacing. So let us give that Excel sheet in the next class and let us start the design. Okay. Thank you, learners.